Welcome to this explainer. Today we're taking a stack of seriously dense meteorological student data and turning it into, well, a high-stakes sky survival guide. We're going to decode the invisible dynamics of the atmosphere so you can understand exactly what pilots are facing when they launch into the unknown. Learning meteorology doesn't have to be some dry science lecture. It's really all about anticipating these invisible forces and knowing exactly how to stay alive up there. Okay, let's dive right in.
Before we actually take off, let's just do a quick pre-flight briefing. We've mapped out our virtual flight from the runway all the way up to the stratosphere, and then back down through some pretty hazardous descents. We're going to decode the unstable atmosphere, read the cloud dictionary, master global wind systems, survive jet streams and wind shear, and finally, battle ice and thick fog. All right, let's get into it.
Section 1. Decoding the unstable atmosphere. Let's decode the sky. So if you want to understand exactly why a flight gets bumpy, you've absolutely got to lock these two concepts into your brain. First up, we have the dry adiabatic lapse rate, or DALR. Basically, dry air rises and it cools at a totally predictable 3 degrees Celsius per 1,000 feet until its temperature just matches the surrounding air. Simple enough, right? It's just a basic thermal trigger causing low-level turbulence. But take a look at the right side. When you add moisture into the equation, the whole game changes. The saturated adiabatic lapse rate kicks in. Because condensing water actually releases heat, the air cools way slower. That means it stays warmer than the air around it for much longer, and it just keeps on rising. Moisture literally supercharges the whole convective effect. It takes a few standard bumps and turns them into massive instability.
Okay, let's put your survival knowledge to the test with a real quiz question, pulled straight from the notes. When you look up at the sky, atmospheric stability is determined entirely by what specific metric? Do you have an answer in mind?
Well, if you're drawing a blank, don't sweat it. According to the notes, only 53.3% of aviation students actually got this right on their quiz. Kind of wow, right? It just shows you how tricky, but absolutely essential, this concept really is to master.
All right, the crucial answer is the ELR, the environmental lapse rate. Now, while those dry and saturated rates we just talked about apply to a single rising pocket of air, the ELR is the actual, real-world temperature of the atmosphere as you climb. It's the ultimate judge. If the ELR drops off faster than your rising parcel of air cools, while that parcel stays warmer, it keeps pushing up, and boom, you've got a dangerously volatile, totally unstable sky on your hands. Now, just as important as knowing how clouds form is understanding how they die. Breaking these complex processes down makes them unforgettable, so here are the 3 exact ways a cloud dissipates. Step 1, the ambient temperature just goes up. Step 2, entrainment, which honestly is just a fancy meteorological word for the cloud mixing with drier surrounding air, causing it to evaporate. And step 3, air sinking within the cloud itself. That sinking air compresses, it warms up, and it completely kills the moisture.
Moving on to Section 2, reading the cloud dictionary. We're going to read the sky like a book.
Our atmosphere actually bulges out at the equator and shrinks down at the poles. It's definitely not some static, flat ceiling. Take a look at this chart. For high clouds, the ones with the cirro prefix, if you're freezing in the polar regions, you might spot them as low as 3 kilometers up. But down in the tropics, you probably won't see them until you hit like 6 to 18 kilometers. Meanwhile, your low clouds, your classic cumulus and stratus, they mostly just stay parked from the surface up to about 2 kilometers, no matter where you are on the globe. Memorizing these prefixes, like cirro for high, alto for middle, and nimbo for rain, these are literally your cheat codes for visual navigation.
Let's pause our virtual climb for another quick active recall checkpoint. We all know cumuliform clouds, those huge, fluffy, towering vertical ones. But what exactly dictates their monstrous vertical growth? What determines how high they'll actually reach?
You might actually have a good gut feeling about this one. A super impressive 86.7% of students nailed this on their quiz, proving it's a fundamental, well-understood rule of thumb for safe flight routing. And the answer is the thickness of the unstable layer. Remember that environmental lapse rate we just mastered? A cloud is going to keep violently pushing upward for as long as the air inside it stays warmer than the air outside. So the deeper that instability stretches into the atmosphere, the higher those towering cumulonimbus tops are going to explode.
All right, climbing up to Section 3, Mastering Global Wind Systems. Time to master the winds.
As we hit cruising altitude, situational awareness becomes everything. Enter Ballot's law. Honestly, this is one of the most brilliant, actionable rules in meteorology you could possibly memorize. In the Northern Hemisphere, if you're flying or even just standing outside, with the wind hitting your back, the low-pressure area is always going to be on your left.
Since low-pressure systems are exactly where severe weather, fronts, and nasty flying conditions like to congregate, knowing your wind direction instantly reveals where the hidden hazards are.
Taking a macro view of those winds reveals the global wind belts mapped out beautifully here. Up at the top, you've got the polar easterlies, then the upper westerlies, pushing across the mid-latitudes, and the tropical easterlies circling the equator. These winds actually flow parallel to lines of constant pressure height, which meteorologists call isopsies, and they're in this constant tug-of-war, perfectly balancing the pressure gradient force with the Coriolis force from the Earth's spinning. It's like a giant invisible engine.
Now we are entering the real danger zone. Section 4. Surviving jet streams and wind shear. Let's survive the roar.
Time for another checkpoint, and this is a really critical navigation question. Flying straight into the core of a jet stream will drastically alter your ground speed, and worse, it completely exposes you to violent, clear air turbulence. So as a general rule, where exactly is the core of the polar front jet stream hiding?
This one was a literal coin toss for the students in the notes. Exactly a 50% success rate. And honestly, I get it. It's pretty counterintuitive for a lot of people. Because the core is actually located inside the warmer tropical air mass. See, jet streams form right where the pressure gradient between two different air masses is at its absolute steepest, which is usually just below the tropopause. So even though it's called the polar front jet stream, the strongest winds, that dangerous core, actually rest on the warm side of that frontal boundary.
And hey, speaking of turbulence, if you're flying anywhere near mountains, you are exposing yourself to deadly rotor streaming and standing waves. Just look at this diagram. When stable air blows over a mountain range at moderate speeds, it ripples, almost exactly like water flowing over a submerged rock in a river. And right underneath those wave crests, you get rotor clouds. These are spinning, violent vortexes of air near the surface that can completely overpower an aircraft's flight controls. No joke, you want to steer way clear of these.
Which brings us to our final descent. Section 5. Battling ice and thick fog. These are the silent killers.
Knowing the difference between these two types of ice is quite literally a matter of life and death when descending through unstable clouds. First, rime ice. This happens when supercooled water droplets smack into the freezing leading edge of a wing and instantly freeze. It traps a bunch of air, so it's brittle, it's opaque, and it tends to just build forward into the airstream. But clear ice? Now that is terrifying. Here, large supercooled drops hit the wing, but only a tiny fraction freezes on impact. The release of latent heat keeps the rest of the drop liquid just long enough for it to run backward over the top of the wing before it freezes into a heavy, clear, solid sheet. It completely destroys the aerodynamic shape of the wing and adds massive, massive weight. Let's wrap this up with some rapid-fire survival tactics straight from the notes. When you're dealing with extreme weather, absolute avoidance by huge margins is literally your only winning strategy. Always secure weather info and pilot reports. Give convective activity, like thunderstorms, a massive 50 nautical mile wide berth. Keep in mind that your standard weather radar just bounces off water, so it absolutely cannot detect dry, clear air turbulence. You need LiDAR for that. And finally, if you're on approach and you detect the sudden violent wind shear of a microburst, do not try to fly through it. Apply full power immediately and go around.
All right, I'm going to leave you with this final, totally provocative scenario from the end of the quiz notes to really test your newfound meteorological instincts. Think about the mechanical turbulence we discussed, the downdrafts, and your ground speed. Here's the question. Is flight with a headwind toward high ground more hazardous than flight with a tailwind toward high ground? Just picture how the air is violently pushing over those mountain peaks and what that actually means for an aircraft trying to navigate it. I really hope this explainer took these dense notes and turned them into a sky survival guide you won't ever forget. Until next time, keep looking up, stay curious, and fly safe.